The idea of continuity and what makes a function continuous is something that comes up a lot throughout calculus, and it is built on for other ideas like what makes a function differentiable, for example. So it is pretty important, and I recently talked about continuity, what it means by definition, and also what it looks like on a graph in one of my weekly live streams, which I'm doing every Monday night at 5 Pacific, 8 Eastern. And I thought you might find this portion of that live stream pretty helpful, so I wanted to show you that today. This is actually one of the topics I also covered in my complete Calculus 1 package. If you want to check that out, there is a link down in the description below where you can go get that. But without further ado, let's go ahead and jump on into this example. So just wanted to kind of start out here with what the definition of continuity is, or the definition of a function being continuous at a specific point. So in general, we're thinking about what it looks like for some function, some unknown function f of x, and trying to think about basically what it means for this function to be continuous at the point x equals a. So what we're basically in this kind of equation here, this definition, you need to keep in mind that a is actually a number. Even though it is a letter, it represents some constant number. It's not a variable like x is. So for a function to be continuous at this point x equals a, that means that we would need the limit as x approaches that a value of our function f of x to equal f of a. Well, what does that mean? Basically, all that really means, let's think about each side of this equation separately. So we have this limit over here on the left. What this is saying is so imagine we have some function. Let's just say we'll kind of graph it here on a xy axis and think about what's going on here. So let's just say we have some function that looks something like this. So this function is, let's just say we have some a value, which will go right here. We'll say this is x equals a. So basically what we're kind of looking at here is what this function looks like specifically at this x value here. So if you go to this x value, x equals a, and kind of trace that down to our function, we're basically looking at this point right here. We're trying to figure out if this function is continuous there. Well, this left side of our equation here, the limit as x approaches a of f of x, what that's saying is, as if we imagine kind of traveling along our function from both sides, as we get closer and closer to this x value of a, so as we kind of travel down our function here and then travel along our function from the left, as we get closer and closer to this x value of a, what y value are we getting closer and closer to? So what y value, or what output of our function, are we approaching as our x value approaches that a value? So the kind of important thing to point out here is limits don't really care what's happening at that specific point. Limits in general only care about what's happening around that point. So this left side of our equation, this limit, it really doesn't care what's going on our function at this specific x value of x equals a. What it cares about is what's going on as we get really, really close to that x value. Kind of imagine walking along your function or traveling along your function. As our x gets really close to that a value, what's going on? And what that's going to tell us, this limit, is what y value we approach as our x gets really close to that. The flip side of that is what's happening on the right side of our equation here. So the right side of our equation just says f of a, which just means the output you get from plugging in this input a for x, which literally is just going to give us the y coordinate, or the y value of this point right here when x equals a. So that would give us this point here. So basically the idea is, if a function is continuous at this value of x equals a, that means you get the same thing whether you approach that x value from either side or by simply plugging that x value into the function. So basically what's going on around that x value lines up with what's going on at that x value. So that's how you can kind of think of what a continuous function means. If you want to think about what that actually means in terms of, kind of the simplest way to visualize it is if you can draw the whole function without picking up your pen or picking up your pencil. So basically what that means is there's no holes or jumps in your function. Like in this case here, there's no holes or jumps. And as a result, as we get close to some point, we get the same thing as just going to that point on the graph. alternatively, if we think about a function that's not continuous, so let's say we have a function instead that looks like this, and let's say this is our a that we're looking at. So basically this function that is, it has a hole right here, and then instead of the function being defined at that point, it has just this one single point up here. So this function is defined for all x values. You can kind of imagine this going on infinitely in both directions. There is this hole here, but the function is still defined at that point because we have this extra point up here. Well, if you think about what happens as we approach that x value from either side, as we imagine kind of traveling along our function from the left and then traveling along our function from the right, the y value that we approach, that we get really, really close to as our x gets closer and closer to this a, is right here, right? Basically just horizontal from where this hole is. But if we just look at where the function is actually defined at that point, that puts us up here at that actual point. So that would give us something up here. So basically the limit as x goes to a of f of x in this situation over here on the right, that limit is going to give us a y value down here. Whereas on the right side of our equation, just plugging in a into our function f is going to give us an output up here, because this is where the actual function is sitting. So since those don't line up, this function is not continuous at x equals a, because we're not approaching the same point that we actually have on our graph there. So that's really all it means for a function to be continuous at a certain point, and kind of what that looks like graphically. Well, I hope you found that video helpful. If you did, please be sure to hit that like button down below. Subscribe to my channel too while you're down there, because the next video that I'm going to be releasing is going to be building on this idea of continuity and talking about one of the actual uses for it, which is the intermediate value theorem. So be sure to subscribe so you don't miss that next video, and hope to see you then.